So for the agenda today, I'll do a Hudi overview, and then I'll talk about how the record level index allows you to get fresher data faster and provides a fast point lookup for queries. Then I'll talk about how you can use Hudi and DBT to efficiently go from raw data to insights. And then I'll talk about how you can use the Hudi Presto integration for blazing fast queries. So let's do a deep dive into Hudi. How many of you have heard of like the data lakehouse? How many of you have heard about Apache Hudi? Okay, so we have some familiarity here in the audience. So Apache Hudi is much more than just a table format. It serves as a comprehensive platform designed for data ingestion and processing, and it's equipped with a range of features and services aimed at maximizing efficiency for both writing and reading data. So at the foundational level of this platform lies a data lake storage, and this is where all your data resides, whether it's in Parquet or Avro. And upon this, Hudi provides a transactional database layer, and this layer is where Hudi's true power shines. It has multiple table services such as like indexing, concurrency, control, amongst others. And these services collectively offer significant enhancements to data and table management. Table services facilitates the handling of data at scale, indexes help with the speed of data retrieval, and concurrency control ensures that this consistency of data across multiple operations. So after the data has been successfully ingested and managed through the previous layers, Hudi offers the ability to connect this processed data with popular computation engines like Presto. So by facilitating these integration, Hudi allows for efficient and advanced querying of data. One focus of this talk is around the indexing, which is on the transactional layer that I showed here. The other focus is going to be focused around Hudi's ecosystem with using Hudi and DBT to efficiently build refined models, and we'll also dive deeper into Hudi Presto for fast queries. So as an overview, when data is ingested into Hudi, a primary key is generated and records are deduped based on the record keys. After the dedupe stage, the records are indexed and then inserted into a Hudi table. In this talk, we'll be going over the record level index that provides fast upserts and lookups, improving data freshness and query performance. Once data is inside a Hudi table, you can integrate it with DBT to build refined models, or you can use Presto to query data for interactive analytics. And we'll cover how you can use Hudi and DBT and Hudi and Presto to achieve fast analytics. So before we dive into these concepts, we'll cover what Hudi table looks like, because we'll refer to some of these concepts when we talk about the record level index. So once data is inside a Hudi table, the Hudi table kind of looks like this. It consists of what we call file slices, and each file size is a base file, which is in a .parquet format produced at some certain commit or action time, alongside with a set of log files that contain inserts or updates to the base file since the base file was last produced. And a group of file slices is known as a file group. So on the top half of the diagram, when a write comes in, the records are written to the file slices, and each record has a key that is mapped to a particular file group. So let's talk about the advantage of having this particular file layout. From the point of writing data to a Hudi table, if you have multiple table services running alongside the ingestion, the services don't block each other because the multi-version concurrency control mechanism that's offered in Hudi. And from the point of reading data, or querying data from the Hudi table, the file layout allows you to query a particular table from a particular point of time. So at the bottom half of the diagram, we get into the timeline and the metadata. So when records get written into the file group, Hudi's timeline also records what commit action was done at what time. The timeline is located in the structure of the Hudi. There's a .hudi folder, and essentially an event log. So there are different actions that can be recorded on the Hudi timeline, such as the commit clustering, rollback, and so on. And I think a key thing to point out in the Hudi timeline is there are timestamps associated with every action along with some metadata about it. Now in the diagram, the metadata table comes after the timeline. So the metadata table is different from the timeline, and in fact, it's actually an internal merge on read table in the Hudi data table. And the metadata table is a central place for all the files' metadata. So when a commit happens, the metadata table equally gets updated as well. You can think of the metadata table as a big index. The other thing to point out is that Hudi stores state. So in the last slide, we talked about the timeline and the metadata table. So if a record has an update, the timeline and the metadata table get equally updated. And since Hudi maintains a timeline of when an action or write occurred on the Hudi table, you can essentially find out what changes occurred in a time range. From there, you can update downstream applications or tables with just that data using Hudi's incremental framework with its CDC feature. And we'll get into this portion when we talk about Hudi and DBT, but it's important to note that you can actually query, you can just get updated data and populate downstream applications and tables with just that data. So Hudi is proven at massive scale. ByteDance, TikTok, Uber, Walmart, GE, and so many more are using Hudi for their mission-critical apps. In particular, at ByteDance, Hudi is being used at exabyte scale for a single table. And even at this level, Hudi is able to bring down the latency from days to minutes. And one of the ways it's able to do this is through its record level index. So one of the ways you can get fast analytics is leveraging Hudi's record level index, which improves data freshness and query performance for point lookups. So to recap, earlier I had mentioned that this is how data is processed in Hudi, essentially. And we'll be focusing on this part, on the index part, and this is what some of the upcoming slides will talk about. So Hudi already supports different indexes for different use cases, and there are two popular use cases that I've shown here. The first one is updating the dimension table from a user input. And usually this generates a lot of random updates spreading, across most files in the table. And for this, you want to use a simple index for such use case. It simply reads the key from the location from the table and then finds the location. And the second use case, the input events are mostly ordered by the timestamp, and most events will fall into the last few hours or only a small portions of the files that are updated in the whole table. And in this case, you'll want to use the Bloom index because it uses the Bloom filters co-located in the data files to prune files instead of reading all the keys. And this significantly reduces the I/O if only a portion of the files need to be updated. And for large-scale data sets ranging, from tens of terabytes to petabytes, simpler Bloom index might not be performant enough. And this is where you might want to leverage something like the H-based index. So what happens here is that you send key lookups to an external H-based cluster, and it stores the key to location mapping, so the key lookup is pretty fast. But there are a couple of challenges when using some of these indexes at large scale. So in particular, with the simple and Bloom index, you need to read either the keys or the Bloom filters on all the files, and they have to read some data or metadata per file. And when you're getting into large data sets, it can be particularly expensive because cloud storage enforces a rate limiting on I/O, which means that you can only send certain amounts of RPC calls to the cloud storage to read the data. And this can also create some bottlenecks to the index. In particular, for the H-based index, although it's performant for large data, you have to maintain a separate H-based cluster. And H-based can be operationally difficult to manage, and it requires some dedicated resources and expertise, so it might be limiting in some organizations. So the next question is, can we design a new index to address both of these challenges? And this is where the record level index comes in. So by design, the record level index stores the key to location mapping like the H-based index does directly on the table level metadata. So you do not need to maintain an external H-base or any sort of cluster in that matter. And to realize that, there's a new partition called the record index that's created internally to store the mapping and the index metadata in a few file groups instead of co-locating with other data files. So this is one way to kind of reduce the file I/O costs. To make the storage footprint low, there's an efficient key to location entry, so a combination of random UID keys and date string partition only take about 50 to 55 bytes. And then the record level index directly leverages the metadata table for fast index updates and lookups. So the metadata table is an internal merge on read table on Hudi that provides uniformly fast updates for different index metadata. The metadata table has an H file format, and that's how you get fast point lookups. So let's look at the mechanism of how the record level index works for both reading and writing data. The record level index is stored in a record index partition in the metadata table with multiple file groups, just like a normal Hudi table. And each file group contains multiple file sizes, and the latest file size reflects the latest snapshot. Given that a metadata table uses the H file as the base format, the H file contains the key to value pairs of the record key to location mapping. So let's say we have a set of record keys to look up. The corresponding file groups are identified by the hash function, and then these keys are looked up in the H file through a point lookup without having to scan the whole file, which is efficient. And then when there are updates to the record level index, the metadata table internally writes new log files with the updates. And during the lookups, both the base and log files are scanned in the point lookup way. The metadata table also periodically compacts the data into file groups to make sure that the performance of reading the record level index is good. So we've done a few performance benchmarks on both reading and writing to demonstrate the performance benefits of the record level index. So compared to Global Simple, the write latency was improved by 2x and the index lookup was improved by 17x. And compared to data with no record level index, the one with the record level index provided 3x and 2x in select and delete statements. So basically the SQL latency and point lookups were improved. The record level index is available in Hudi 0.14.0. And if you're interested in learning more, you can give it a try. So next, we're going to transition into a study in the medallion architecture with Hudi and incremental processing with DBT. So Hudi can integrate with DBT to build refined data models, and this is another way that you can get fast analytics. So incremental processing typically begins with extracting data from an upstream data source like Kafka and loading the raw data into a lakehouse storage. So from the raw data or bronze stage onwards, there will be many transformation jobs orchestrated in different cadences to move data across different tables or in the lakehouse platform. But when the number of these jobs grow, it will be super critical for organizations to be able to conveniently deploy and operate them. So DBT stands for the Data Build Tool. It's designed to handle transformations, it's basically the T in the ELT architecture, and it standardizes the way to structure and manage SQL and config files, and does the heavy lifting for connecting and building up data pipelines. There will be links in the presentation. You can refer to the links to learn more after the presentation. So this is what a typical DBT project looks like. The DBT project.yaml file defines the context for the whole project, and it usually involves a bunch of data pipelines that depend on or are closely related to each other. So the structure contains a version information, project folder paths, common settings, and so on. And models in DBT represent the transformations and involved groups of datasets or tables of the lakehouse platform. So the model folder contains the definitions of all the datasets involved by the transformation pipelines and how the transformation logic looks between the datasets. The target folder is generated upon the project build, and it contains compiled and runtime SQLs that DBT generates based on user-defined models. So whenever a user chooses to update some models or settings, content in the target folder will be updated after the build or run command. So we'll walk through an example, a use case to illustrate DBT usage with Hudi's incremental processing feature. So the sample dataset is very simple. The upstream data contains user profile updates. Specifically, it contains the updated city and a timestamp for a particular user. The first transformation process, the raw updates and upserts into a Hudi table to give the latest state of the city information for all the users. The second transformation pulls the changed user profiles corresponding change information to allow the downstream jobs to react. For example, there could be some popular live events planned in some city X. And if the users who recently changed their profile and updated the city field from other cities to city X, the system can grab all the users and send the recommendation emails to help the event promotion. The SQL file, which is the raw_updates.sql, is the first SQL defined in the project, and it's mocking the data ingestion portion, basically. But in a full-fledged setup, the table would have been populated with upstream data sources like Kafka. In this sample project, the source data is hard-coded for illustrative purposes. But when we execute this transformation, we'll bootstrap a table called raw_updates that contain 3 records, user 101, 102, and 103, and they have the set city set to A, B, and C. To simulate new updates, we can run an insert command, and shown here, we can update their cities to D, E, F, respectively. And if you look on the far right of the diagram, you can see the cities being updated. The example code is available, so again, you can find more about this project after the presentation. The second transformation process is the raw updates incrementally and creates a profile table for all users. So the profile table is a Hudi table that contains the latest city information. So to highlight some important settings, since we want to analyze what records were updated in the subsequent transformation, we should enable the CDC feature in Hudi by enabling hudi.table.cdc.enabled. And this will make the writers to log the record changes along with the upserts. So in the code on the bottom half of the left-hand side, the gray box, there is this is_incremental macro near the bottom part that indicates only the data newer than the latest records in the profile table will be processed. So you're only grabbing the changed data. And this is one way to realize the incremental nature of the job. So if we go back to the earlier presentation, we talk about how Hudi maintains state, and we talk about running an incremental query with just the range of time that you're interested in. This is very much the same what we're talking about here. So also note that the incremental strategies, incremental strategy is set to merge, and meaning that the merge into SQL statements will be generated to fulfill the upsert semantics in Hudi. And the merge _update column indicates the table fields to be updated through the merge. And the last transformation is about pulling CDC records from the previous Hudi table profile into a new table called profile_changes. So to highlight some key parts, the Hudi_table_changes is a table valued function that's newly been added since Hudi 0.14.0, and it's designed for doing incremental queries with SQL for Hudi tables. In this example, the CDC mode and a begin time of 1 day ago are passed into the function, instructing the query to pull all the record changes, including before and after images during the last 24 hours. So when you grab the before and after images, if we go back to the user, we have the before images of, I think, user 101 was city A, and then the after image is they were updated to city D. So you can grab these two images and then use that data to populate downstream tables or use that data however you want to use it. So the result from the CDC incremental query contains JSON formatted columns named before and after, and depending on the configured CDC logging level, you can get that out. So these columns contain the complete images of the record before and after images, and we can extract the relevant record fields to basically use it for whatever we want. So if we go back to this to the use case, if we want to promote events in the target city, the promotion can be time sensitive, and so we only want to apply these promotions to people who have recently changed their city. So doing Hudi CDC incremental queries will make sure that only process relevant records instead of scanning the whole user profile table and then filter down what is exactly required. And this can potentially save a great amount of data I/O, bills, and obviously lead to faster analytics. DBT also supports generating documentation UI pages for easily browsing the project datasets. So when there are hundreds or thousands of datasets in transformation, it's kind of a must-have feature in order to efficiently navigate through, these transformations and data to locate exactly what you might need. So to recap, with DBT and Hudi, DBT naturally supports building incremental pipelines with merge semantics. Hudi CDC feature produces before and after images of changed records, allowing for rich data transformation. And with incremental processing in DBT, we can cut down on processing costs by limiting the amount of I/O and only process relevant data. So an example, we mentioned that we can avoid full table scans to just process the change and updated data. So the next way that you can get fast analytics is using Hudi with Presto. So Presto provides a rich set of connectors and APIs through which we can integrate the Hudi metadata within the Presto connector to optimize the query plan. So for instance, if we want to list a partition, typically you'll have to prune the partition. You want to only list 10 partitions of like the 1,000 partitions available, depending on the query predicate. So in order to figure out what files to scan in absence of the Hudi metadata and after partition pruning, you'll have to go and list each of those qualified candidate partitions. And this can be costly. So with the Hudi metadata, what the Hudi metadata does is it saves on some of the I/O costs by storing this mapping from partition to files in the files index. And in this diagram, I'm showing that basically the Presto connector is able to read that Hudi metadata and avoid listing the partitions directly. After, it distributes the work once it has planned the query to the Presto worker so each one of them can operate on some chunk of data. So in this slide, we're zooming into the diagram from the first slide. The Hudi metadata also stores the column stats, where you have a data by column partition and file, and the statistics of the min, max, and null values. So the Hudi split manager with the Presto Hudi connector, when it passes the constraints to the tuple domain, it pushes those predicates down to the Hudi file skipping manager, which can talk to the metadata reader and essentially do a couple of things. It can range read on how the column stats, it can do a prefix lookups on the column stats, and it can figure out which files do we really need to scan. In here, the tuple domain is nothing but the predicates that you have in the query. So first level within the partition, we want to know that there are 10,000 partitions. But after partition pruning, Presto only needs to scan, let's say, 100 partitions for a particular query. So let's say within each of those 100 partitions, there are 10 files. So altogether, there are about 1,000 files that need to be scanned. Using the column stats, even within those 1,000 files, you can skip certain data. So let's say you had a query predicate apart from the partition filter. Let's say you had another filter on some data, column C1, that is greater than or equal to 100. And let's say C1 is a numeric type column. After the file index has been utilized to figure out what files need to be scanned further, you look into the call stats and figure out that those partitions, precisely what are the files that contain the data from column C1 that is greater than or equal to 100. And then instead of actually scanning the whole 1,000 files, you just may end up scanning, for example, 100 files. So this again saves on a lot of the I/O costs, especially if you're on cloud, and it also helps improve the query latency. There are benchmarks which was done on the GitHub archive dataset, and these are different layouts, but basically one is where you have done no optimization. You just are ingesting records into Hudi, you have no clustering, you don't have any column stats, and this non-optimization is represented by the blue bar. As you can see, if you have clustered the data and also build call stats, then you can see with the red and yellow columns that the query latency has decreased, so the query performance has improved. So we're working on looking forward with the Hudi Presto integration, we're working on supporting the record level index. We're also working on supporting the secondary index support where search keys are not unique. And we're also working on the incremental and time travel queries as well. And finally, we're working on advanced caching techniques. Specifically in Hudi, we've recently released 1.0.0-beta, and this release features highlights some game-changing features. So Hudi now supports non-blocking concurrency control for high streaming writes. So allows for multiple writers to operate on the table with non-blocking conflict resolution, thereby reducing wait times and avoiding bottlenecks. And it's basically ideal for high streaming writes, whether you're working with Flink, CDC, Spark, and more. Hudi also now supports functional indexes, so it's built on top of Hudi's multimodal indexing subsystem, and essentially an index on a function applied to a column, and enhances access speed and integrates partitioning into the indexing process. You can easily manage these indexes using familiar SQL syntax, and you can build multiple indexes based on the function defined on the columns. So you can write a SQL statement like create index on some table name, and then you can provide the column name and the key and values that you want. You can learn more about the 1.0.0 releases with RFC 69. It's a link to the GitHub issue that has more details around that. If you want to learn more and build with us, you can scan the QR code to join the Hudi community channel. We also, if you visit our site, you can find more information in docs and blogs. And you can follow us definitely on LinkedIn and Twitter. And I'm happy to go ahead and take some questions.